Hello, everyone. Today we're going to be talking about the different gas laws, including Boyle's law, Charles' law, Gay-Lussac's law, and Avogadro's law. Before we discuss all of those different laws, we need to discuss what the difference between direct and indirect relationships are. A direct relationship is where one variable goes up and the other goes up. So if I increase one aspect of my equation, then that means that the other thing is going to increase. Or if I decrease something, then the other thing is going to decrease. An inverse or indirect relationship is where you have opposites. So as I increase something, or as one thing goes up, then the other thing is going to go down or decrease, and vice versa. If I decrease, then the other thing is going to increase. And so we refer to all of these laws as either direct relationships or indirect or inverse relationships. The first law that we have to talk about is Boyle's law. Boyle's law says that pressure and volume are inversely related. And so as we increase the pressure of something, the volume decreases and vice versa. We can decrease the pressure and the volume will increase. So think about different things in your daily life, maybe even just like a can of soda. If you were to squeeze a can of soda, causing the sides to cave in, what you're doing is you're decreasing the volume that's in that can. And so what's going to happen is the pressure in that can is going to increase until it reaches a point where you've decreased the volume enough that the can explodes due to the pressure. And so in that case, we were decreasing the volume by squeezing it, and our pressure was increasing. And so pressure and volume have inverse relationships. So you'll see the equation there, P1 times V1 equals P2 times V2. So if I have my original pressure, my original volume, and I say that I decrease it by a certain amount, so I get a new volume, then you can solve for your pressure. All you're doing here is using simple algebra, similar to what you did with the MV equation these last couple weeks, but these are pressures and volumes instead of molarities and volumes. A graph of Boyle's law is shown here. So as you can see, we have volume on the y-axis and pressure on the x-axis. And so you'll notice that as the pressure is increasing, our volume is going down. And so when we increase that pressure, that means that there's less space for our gas molecules to move around. These next two gas laws that we're going to talk about use Kelvin as the temperature scale. You are probably more familiar with Celsius and Fahrenheit. Kelvin is a scale that we use in chemistry in order for all of our temperatures to always be positive. It makes our mathematical calculations a lot more simple. And so it starts off basically at what's called absolute zero and then just goes up from there. So you are familiar with Celsius and Fahrenheit. In science, we do not use Fahrenheit very often. Mostly you'll see in Celsius. And so if a problem gives you the temperature in Celsius, then you just need to add 273 to that Celsius temperature in order to get your temperature in Kelvin. So just make sure that you convert your temperatures before you put your information into the formula. You don't want to convert the temperatures after. You need to do that before. Otherwise, your numbers won't come out right because, like I said, sometimes using Celsius, we get negative temperatures, and we don't want to use those negative numbers in our calculations. Charles' law is our first example of a direct relationship. Charles' law refers to volume and temperature. So for a direct relationship, as my volume goes up, then my temperature also goes up and vice versa. And so normally you see this opposite. You see this as we increase temperature. So if you think of a balloon, if you take the gas molecules that are in that balloon and you heat them up and you increase the temperature, the volume of the balloon is going to go up because those gas molecules that are in that balloon are pushing more on the outsides of the balloon. And then you could also see the opposite. If I take a balloon out into the cold, the volume of that balloon is actually going to shrink because the temperature outside in the cold is slowing those molecules down, so they're not going to be pushing out on the sides of the balloon as much. So you'll want to use the formula B1 over T1 equals V2 over T2. So you're going to take what your initial volume, let's say in the balloon example, you take your initial volume of your balloon and your initial temperature of your balloon, and you'll take what the temperature outside is for your second temperature, your T2, and then you could calculate what the volume of the balloon is going to be when you walk outside. And we already know, though, because our temperature went down as we went outside, then our volume will have decreased, but you can actually solve to find the number. But don't forget, on your temperatures, you need to add 273 to any temperatures that you're given in Celsius. If they give the temperatures to you in Kelvin, then you're good to go. You can plug in, but make sure that your temperatures are in Kelvin. This graph here shows the relationship for Charles' law between volume and temperature. So as you can see, we have a direct relationship here. So as our volume is going up, our temperature is also increasing, and so you can see that positive correlation here on the graph. The next law that we need to talk about is Gay-Lussac's law. It is very similar to Charles' law, and instead of volume, we are now talking about pressure. So Gay-Lussac's law says that pressure and temperature are directly related. And so as I increase my temperature, I'm going to increase the pressure. So if you think of some type of canister that has gas, similar to maybe some hairspray, they often say you don't want to store cans of hairspray out in the heat, because as you increase the temperature of the gas within that can, you're increasing the pressure within that can, which could cause the can to burst. And so those two things have a direct relationship. As I increase temperature, my pressure increases. As I decrease temperature, my pressure decreases. So on this one, you will also want to make sure that your temperatures are in Kelvin. So anytime you're given your temperatures in degrees Celsius, you'll want to convert those to Kelvin and then plug them in. So as you can see in the example here on the slide, if I have a gas that's at a temperature of 200 Kelvin in 1 atmosphere, if I increase that temperature to 400 Kelvin, you can plug that into this equation, P1 over T1 equals P2 over T2, and you will solve and find out that the pressure is now 2 atmospheres. So because I doubled my temperature, I also doubled my pressure, and so there's a lot more pressure in the second cylinder than there was in the first. This shows you a graph of the pressure and temperature. It should look very familiar to you because it looks just like the volume versus temperature graph. In that we have a direct correlation. So as we increase our temperature, our pressure also increases. And so we show kind of graphically that this does have a direct positive correlation. If we need to, we can combine all 3 of these gas laws, Boyle's law, Charles' law, and Gay-Lussac's law, into one law called the combined gas law. It basically combines all 3 gas laws into one formula. So what makes this nice is that you can use the combined gas law, and then if something remains constant, you can leave it out. So if you notice, P1V1 equals P2V2 is also within here, and you can see the relationships P over T equals P over T, and V over T equals V over T. So you can either choose to remember all 3 formulas individually, or you could memorize this formula and then just leave out whichever of the constants or whichever of the variables remain constant. And so in this case, let's say my volume didn't change, I would just leave it out of the equation, leaving me with the P over T equals P over T. In this case, you still want to make sure that your temperature is in Kelvin, but this is just an easy way. It's not its own separate law, it's just a combined into one. Sometimes you might change multiple things. You might change pressure and volume, and you want to see what happens to the temperature. And so in that case, you would want to use this combined gas law as well. The last law is Avogadro's law. This one tells us that volume and moles are directly related. This one is more intuitive. So if I have an increase in the number of moles, meaning in simple terms, it's just increasing the number of stuff that's in my container. Increasing that will increase the volume. If you think about it, basically the more particles of gas, the more things I put into my balloon, the more that the balloon increases in volume. As you blow a balloon full of air, as you increase that amount of air that's in there, obviously you can see that the balloon increases in volume. And so this basically just tells us that there's a direct relationship there. So as I increase those number of moles, which we denote using N as our number of moles, as I increase the number of moles, that's going to increase my volume. So I can use the relationship V over N equals V over N. So just to review everything that we've talked about, we learned that pressure and volume are inversely related. So as I increase my volume, then I'm going to decrease my pressure and vice versa. Volume and temperature, as long as you have your temperature in Kelvin, are directly related. So if I increase the temperature of something, my volume is going to naturally increase as well. Pressure and temperature, as long as your temperature is in Kelvin, are also directly related. So if I decrease the temperature of something, then I'm going to decrease the pressure. So those have a direct relationship. And then lastly, volume and N, the number of moles, are directly related. So as I increase the number of moles or the number of particles that I have, I'm also going to increase that volume. So just make sure, do not forget, because this is the most common mistake, that for all equations that involve temperature, you have to change that temperature to Kelvin. So if you're given it in degree C, you want to add 273 to your degree C, and that will give you your temperature in Kelvin.